Yes, we have 3 minutes. Actually, we're going to do a small presentation just before your presentation. You'll get 5 minutes.
So should we put up the slides?
Okay. We don't need any slides. So we'll have to be out of here exactly at 12.
Vi synes Amy Stetson over dit.
It's tired.
It's tired of all the
And then lunch is 12 to 2. And then I can hear you. Well, I was going to, but it hasn't been clear. Please don't stop. Can you turn the lights back on?
Yes.
Yep, the most level I assume you do pretty high in the morning. Pretty high in the day.
Yeah. Are you happy with it? No one has to
It's really hard. Never had lobster. You choose. Yeah, it was 10 minutes. Really barbaric. Crushing.
Like,
You don't think that would be
everything is
refined food.
The Gucci is
it was going to be the last time that he would.
As long as
Oh, that was before my time, but yeah, I think, 4 years ago, it was the lobster one. So they're fighting?
Yeah, because in Iraq, like that, the lobster. Something very No way.
I would give you Harvard time, 5 minutes past the hour, so I give it 1 more minute.
Okay. I don't think it's on the ocean, right? The lobster. And what's on the oysters?
Oh, sorry, yeah.
They're very good and
We're in my winter boots now.
think about it how long the last time.
No.
No, I used to be
Can you use the call mic? Excuse me. Excuse me.
Every time one lobster, one fish.
Sure.
the fever, the fever straight through the next day.
Use the mic?
We're splitting it.
I think he's trying to get your attention. No, he's just going to put
No,
the
I
mic
was
on.
Boston, but since then, I still suffer from jet lag, so I don't want
Test.
to.
Okay. So good morning, everyone. So we are slowly moving out to galaxies from small scales to large scales. So we start the morning with Stefan Reisel. He'll talk about synthetic observations or radiative transfer tools.
Can you hear me? Yeah. So So good morning, everyone. Thanks for having me. So what I'm going to present today is a more detailed overview about the physics and the numerical concepts of creating synthetic observations, and after that I'll provide plenty of examples what kind of science you can do with that. So nowadays we are getting all these exciting MHD simulations, including turbulence, magnetic fields, even chemistry. You've heard it all. And from the observers, we're getting all these beautiful observations. But in order to test how good our observations are and how predictive our models, we need somehow to connect these two fields of research, and this is basically what I do for a living. So in my research I'm following questions related to radiative transfer techniques and the physics of polarization in order to create synthetic observations. So first of all, we start at the very basics. So in the most simplest case, you have your intensity, you have your source term and also some extinction, and then you can calculate how your radiation propagates through the medium. This can be analytically solved by introducing the optical depth. So then we are basically done, right? But then you get a density distribution like this, where we have direct radiation. The light radiation might scatter multiple times, and you can even have reprocessing of the radiation by, let's say, absorption and re-emission. So the question is, what is the radiation field at each of these points? And one way to tackle this is the Monte Carlo method. It's somehow related to gambling. It's a method based on random numbers. However, it's not random. It follows certain rules like all of these games. And what it looks like in detail. So for example, you have a source, a star, and then you have a probability distribution, let's say, for the wavelength. So you sample a photon, then you sample an optical depth from some kind of rule, and then you propagate your radiation through the medium, or let's say a grid, until the photon leaves your grid. So you're going through this loop until the photon is gone, and then you sample a new photon until you run out of photons. And this allows you to calculate the radiation field in each of your grid cells. So this has many applications. For example, you can calculate dust heating, the grain alignment efficiency, or let's say the level population of different gas species. So, but radiation has more to offer than just the intensity. You can also learn a lot of physics from observing polarization. One way to quantify or mathematically express polarization is with the help of the Stokes vector. So you have your electric field vector, and you can express it in different kinds of coordinate systems, which gives you then the Stokes parameters. I is the total intensity, Q and U is for linear polarization, and V is for circular polarization. So you might ask, why do it this weird way? But if you have different contributions, let's say from different polarization effects, then you can just take the sum of different Stokes vectors once you have them. And then you can calculate polarization degrees or orientation angles of the polarization vectors. But this requires then to reformulate the radiative transfer equation, where intensity gets the Stokes vector, the source term is then also some kind of vector, and the extinction is described by the 4x4 Miller matrix. So if you want to have any radiative transfer modeling involving polarization, we need to know what our Miller matrix is. And here's one example of that. for aligned dust grains. So the way people believe this works is that the dust grains spin up by radiation. Then for paramagnetic grains, they couple with the shorter axis to the magnetic field direction. Then here we have some kind of polarization, for example, in emission. So this allows us to trace the orientation of the magnetic field, given that we know what our Miller matrix is. And the way to do it is that you can pre-calculate your cross-sections of extinction and polarization and absorption. Then you integrate over some size distribution for your dust grain sizes, different materials, and take also into account the grain alignment efficiency. And then you get a Miller matrix like this, where the subsystem describes the transfer from intensity into linear polarization. You have also some transfer into circular polarization because of birefringence of the dust grain, but you can do this kind of exercise for many different traces, for example for synchrotron radiation. Yet again our magnetic field, and we have some high energy cosmic ray electrons forced on an orbit around the magnetic field lines, emitting some polarized radiation. Here you can calculate your transfer coefficients by assuming a distribution of energy of your electrons, where P is the power law index and the gammas are your Lorentz factors and some gamma functions. But what we have here, we have again our transfer from intensity to linear and circular polarization, but we have also these off-diagonal elements which describes the Faraday rotation. So the way how this works is you have a polarized radiation running into an area with 3 electrons, and then your polarization vector rotates, and this is related to the magnetic field strength. So this provides you some estimate of the magnetic field strength. Finally, you can also do this with line polarization. So in the presence of a magnetic field, your levels split up, or some of the levels split up, giving you this pi and sigma transitions. So here we have the total intensity and the contributions of the different sublevels. The pi is related to linear polarization and the sigmas to circular polarization. Here you need all to know these line strengths of all the different sub-level transitions. This describes your line broadening, and this is the matrix that describes the angular dependencies of all these transitions with respect to magnetic field and the observer. So once, you can calculate this doing some quantum mechanics, this gives you your Miller matrix again, and here you have also a dependency on the magnetic field. So if you measure the shift here between all these transitions, you can also learn something about the magnetic field strength. Of course, these systems of equations are no longer solvable analytically, in general. So the way we do it, first of all, we determine for creating a synthetic image how many rays do we actually need to resolve all the regions. So low resolution regions do not require that many rays, whereas high resolutions regions get more rays. So this comes with no cost, and then for each of these rays we solve the radiative transfer equation as I've outlined before. Then we do some kind of interpolation that is especially relevant for line polarization, and finally we use the Runge-Kutta-Fehlberg solver. This is a 4th order solver with a 5th order error correction. That means we have a variable step width to solve then the radiative transfer problem for all of our quantities along the line of sight.
Is that actually is 3D, right? On the left?
This is 3D, yeah. So let me say a few words about the grid, the choice of grids. So we have some kind of predefined problem. We might exploit some symmetries, or you have some data from a MHD simulation, so your grid is predefined, and then you use a tool that has just a limited choice of grid geometry. So then you might be thinking it's a good idea to match one grid geometry into another, and this is some exercise I did in my PhD thesis, but we had a similar problem very recently, and here you see the ratio of the emission of this exercise, and here you see all these kinds of artificial signals you get just by using the wrong grid geometry. So the message here is don't do that, use always the original grid. So there are many codes that can solve these kinds of radiative transfer equations. There's the Polaris code. It's a code I started while doing my PhD thesis, and then many people contributed, and so it's now a full radiative transfer code that has all the features I've outlined so far. The Monte Carlo dust heating, that can read in different dust models. We spend a lot of effort in the grain alignment physics. You can define all kinds of different sources for a radiative transfer process. Then you have the dust, the line, and the synchrotron polarization, some optimization techniques, so you can, the radiative transfer and the Monte Carlo can easily be parallelized, and we have all kinds of native grids so that you can read in data from different simulations directly. And the red points here is work, ongoing work, where people are expanding the code right now. Okay, that's that. And then what kind of research we are doing with radiative transfer modeling. So first, some reminder of the theory. So here's all the ways the dust grains can align with the magnetic field directions and the way the magnetic field may be orientated along the line of sight. And for all these configurations, your linear and circular dust polarization may get enhanced or cancelled out. So doing dust polarization may give you some clue about the magnetic field morphology. And the same for Zeeman effect and the Faraday rotation measurement. I both trace the line of sight magnetic field strength. So you may not just be interested what is the magnetic field strength in some kind of astrophysical system, but also maybe you want to know more about the history and how the magnetic field is warped. So this might be a good idea to exploit these kind of tracers to infer the magnetic field morphology. I guess I've shown the slides at the last Harvard Heidelberg meeting where we investigated what's going on in filaments. So you have all kind of claims and observations. So for stability arguments, you may have some kind of helical fields, but you can also imagine that the filament moves through magnetic field lines, dragging the lines with them. And then we looked into this in detail to find out how can we distinguish all these cases. And here we see the polarization pattern for different field morphology models and inclination angles, and also the profiles of linear and circular polarization. Here you can see that completely different morphologies may have very similar polarization pattern. So it's very indistinguishable by observation. So we did also here some Zeeman calculation and find out in dust polarization in combination with Zeeman, we might actually say what kind of morphology this is. And we had some discussion about the formation of filaments. So this picture of Inoue and Fouquet is that some blob runs into some high density region, dragging the magnetic field lines with it, and then the filament forms outward of the screen. This is already something we had modeled, but we are interested if we can actually trace this in a more realistic environment. So luckily we found such a filament in one of Steffi Weich's silk simulations. So here you have the density distribution of this isolated filament. You have the mid-plane cuts, so you have the velocity shocking here at the filament, and the most important thing is that you have actually these kind of predicted magnetic field lines. So we use...
Could you just go back one? Could you explain? That's a 3D plot. What view is
These are
that?
mid-plane cuts, so we are cutting here through the filament. So that here, this is the spine, and here the spine is in this direction.
Into this grid.
Yeah.
Okay.
So we use the full power of Polaris to see if we can actually learn something from such an environment. We derive the column density. Here's the spine of these isolated filaments. And then the first surprise was we had this profiles from our numerical models, but we couldn't find them in all of the places here in linear polarization. So here are the predictions of our models, these shaded areas, and we just can find traces of this bent magnetic field in 3 distinct areas, and for the circular polarization it doesn't work at all because of the turbulence of the magnetic field. But now we had also this feature of synchrotron and Faraday rotation. So with Zeeman and Faraday rotation you can derive the magnetic field strength. So here you have the original field from the MHD, where we did just the average through each cell. And here's the one derived from a Zeeman observation, which matches very well, but here we have some over-prediction of the magnetic field strength, and here's the same map for the magnetic field strength derived from Faraday rotation. And the nice thing is we get a sign, so we know here it goes away from us, and here the magnetic field comes in our direction. So here's a histogram. So Faraday is someone under-predicting the field strength, Zeeman is over-predicting, but this is just for this particular case. But in the line profiles we see that we can't learn anything, because you cannot assign this line profiles to any particular magnetic field morphology. They can get the strength, they can get the direction, but it's really hard to tell which morphology it actually is. So that's that. We are also working on all kinds of simulations and models of the Milky Way. So one project I did with Simon and Eric Pellegrini was what we can learn about the Milky Way from synthetic observations. So we took the galaxy AU6, which is part of the Auriga project. So the Auriga project is a cosmological box simulation, and we took the most Milky Way-like galaxy, and then we populated this galaxy with a population of clusters. So we developed this population synthesis method, and with that we can then derive quantities that are not in the original simulation itself. So we recalculated the electron fraction and also the H-alpha emissivity, for example. So on one outcome of this kind of modeling was the reddening of line observations. So we may do some observations of lines, for example, to learn something about the star formation efficiency, but all your lines, or some of the lines may be screwed by dust absorption. So what we did is we calculated the H-alpha emission with dust, then can correct it by this ratio of H-alpha and H-beta observation. So this is our rednet map. But we now had the luxury to actually switch off the dust completely and to see how good these dereddening techniques actually work. And here you can see the ratio where the grayish stuff is, where the difference is in the order of unity, but you have also all these regions where it doesn't work at all. Here you can see the ratio going with radius, and for more for more edge-on galaxies, it gets even worse. So we had this population synthesis. And then you look here, for example, in the radial and profiles along the z-axis, and you see that we are very well within the range of other predictions of the electron fluctuations of the Milky Way. You may wonder what this is actually good, and this is not so much about the distribution of electrons in general, but more about the small scale structure. So what we have here is a H-alpha map of the Milky Way. Here's our prediction derived from the Auriga simulation. By the way, we have here, for example, a sulfur-3 mission, so we can predict lines for which no observations exist so far. And of course, you cannot derive the quantity by a pixel-to-pixel comparison. So the way you can do it is to decompose your map into spherical harmonics to derive these coefficients and functions. And what this means is that for smaller L you have large scale, and here you have small scale features. And here you see the red area. This is for our predictions of the Milky Way in H-alpha, and the blue line is what we know from seeing actual observations. And what the advantage of this method is that we can actually account for the emission in different scales. So we did the same exercise in a synchrotron. And then we saw, okay, we are missing a lot of the small scale features, but the synchrotron is related to the cosmic rays and the magnetic field. So we tried different way of finding out how what is missing in our modeling, and then we saw what kind of parameters for the cosmic ray distribution and the turbulence of the small scale turbulence of the magnetic field might actually improve our simulations, our modeling, and this is one way to quantify how good MHD simulations actually are by doing this kind of radiative post-processing. And finally, we did also this in a Faraday rotation. So Ralph Klessen always likes to fool its audience by asking which one is our model and which one is the Milky Way, but I'm spoiling it for you. This one is the Milky Way. And what you see here, for example, going along the longitude, is here you have the transition going from positive to negative, and this is due to the toroidal magnetic field component in the Milky Way, where on the one hand side the field is pointing in your direction, then the field is pointing into the other direction. So we can reproduce that, but here in the blue line you see previous attempts to model the Faraday rotation map of the Milky Way, and you see here there's some small scale structure missing, but with our kind of modeling we actually can account even for the small scale structures. This is the advantage of this kind of modeling. So I have 10 more minutes, right? So another project we are following is what is going on in our own Milky Way with respect to the spiral arms. So as we've learned yesterday, this is what the Milky Way looks like. But how do we know, since we are in the Milky Way and do not have this view from the outside? So you can actually count the tangent points in different traces, but how reliable are these traces and what role does play our solar neighborhood? This is some kind of questions we are following here. So the Auriga galaxy was not suitable for this task, so we created especially for this purpose, a new kind of simulation where we have well-defined spiral arms, and we have also some kind of supernova feedback. So this means we can model the bubbles around the observer position at different stages of its development. So here is the electron fraction and the magnetic field, for example. So then we did all kind of analysis for different tracers, for example, multi-wavelength maps of the dust, but also for different lines and the synchrotron emission. So one way to determine the tangent points of spiral arms is by looking at the longitude velocity diagram. So this is CO for our own Milky Way. And as you go for the observer along the spiral arms, you can trace these kinds of loops, and the tangent points are in this turning point. So we did the same. So this is one map we derived, and from that we can count the spiral arms in our model galaxy. You can also do this in other tracers, for example in dust, in synchrotron. Here we have the longitudinal profiles and the intensity, but also in Faraday rotation. So we have here all predictions of Faraday rotation and how good it matches for all the other synthetic tracers we investigated. And one thing we saw, that we always have this kind of line shapes, so it rises and then runs into some kind of plateau. You can see it even better here. And then we wondered, okay, is this some kind of characteristic feature? And the way we explain it is with some simple geometrical argument. So we have these Faraday rotation data from the source survey, and this is actually how this project started, because I've been asked, can you explain this kind of shape of the data? And then we see here for our modeling, we see that it rises and then runs into some kind of plateau, and this is the way we interpret it, is this is actually just geometry for spiral arms that you run through your spiral arms. Of course, this is modulated by densities and temperatures, magnetic field, and so on, but this is the way we see it. And finally, what is the influence of our local environment in the Milky Way in observing all these kinds of spiral arm tracers? So we have here the observer at the position 1, which is a bubble that is most similar to our own local bubble, and then we have here the tangent points detections for all the different tracers, and some are more closer together than others. And one way to quantify is how many detections do we actually have for different observer positions. So the local bubble that is close to our own local bubble in the Milky Way has the most detections, and also that we have the range, how much these different tracers differ from each other, is also the best for the observer position P1. So this is actually already it, what I've prepared for today. So I've thrown many different concepts and topics and projects in your direction, and hopefully there was something interesting for each of you that you can pick up. And then all that remains to say is thanks for your attention.
Thank you very much, Stefan. So we have 15 minutes for discussion. So, Annalisa?
Yes. Can you expand a little bit about the assumptions you make on the dust, on both the filament exercise from the SIRT project and the Milky Way observation? So I'm sure from in the Auriga galaxies, my colleagues do not self-consistently model the dust, and therefore you have to make assumptions about how it is distributed, what geometry, what kind of dust grains, etc. And so I was wondering whether you can tell us a bit more also for the filaments here in the
Yeah, for the filaments, I mean, you have your usual distribution of grain sizes and materials for the diffuse ISM, and here we actually use this kind of modeling. but then we assume that there are even larger dust grains closer to the filaments, so it's actually a two-component model where we have smaller grains in the outer parts and towards the filaments. We have the same size distribution, but we go to larger dust grains and towards the center of the filament, and here they are just simple oblate spheroids with a certain aspect ratio.
And what about how much dust is there? I don't know what people assume in this.
Yeah,
smaller
usually it's
scales.
assumed 1%, but it may be different for different kind of environments. But here it's in all the projects I've presented here, it's as an assumption of 1% of dust mass to gas mass. So here we had the metallicity in this kind of simulation, so we have here scaled our dust model with metallicity. And since we did also some radiative transfer processing, then we estimated how much dust is destroyed by radiation close to these clusters. So this is what went into this, but here we also assumed, so we start with 1%, but we had, actually that's a good point, then we had some, doing this dereddening, we had some discrepancies from what we know from the Milky Way also here, but then the mass of this galaxy is a little higher than that of the Milky Way, so we scale this ratio
But
a
indeed,
bit
like
down.
let's say the dust to
but
metal ratio is a free parameter that we need to assume
so
here.
here
Right?
it's a little less than 1%.
To gas mass, not to metal mass.
Yeah,
Okay.
yeah, on average.
Can I ask another thing since we are here? Why do you do this population synthesis, which, given that the Auriga already produce your sources of radiation under the form of stellar particle? So what do you guys mean by population synthesis, and what are you doing there?
Yeah, actually we started here with this kind of Faraday rotation map. We looked into it and wanted to know what's going on, and then we saw that people tried it in literature multiple times to reproduce such a map. And they also did this kind of spherical harmonic expansion, and they all failed that in that sense that from some of the multiple moments actually it drops, so that we had to somehow increase the small scale structure. And this is how we came up with this population synthesis model. So actually assume some kind of star formation history.
So what is it synthesizing? Sorry.
Synthesizing is in that
What
sense
are you making? Are you making
that we get rid of all the zinc particles provided by the MHD simulation,
So
and
the
then
stellar
from the
particles.
other parameters we do some statistical calculations of what the population of different stars might be, and also what is the most likely environment where such a cluster is positioned within the galaxy. This is what population synthesis means, and this is, the electron fraction of the Auriga galaxy is very similar, but what is new that we have actually account for all these ionizations by the cluster, and this is what the advantage of this here. Maybe Simon wants to
Yes,
elaborate on that.
to just follow up on that a bit. I mean, we're basically synthesizing clusters, and we're putting them in with a specified cluster mass function.
Yeah.
So one of the big things that you wouldn't get if you just take the Auriga star particles, is you get all the low mass clusters. Whereas if you just take Auriga, you're limited to whatever minimum resolution of star particle it forms, which is quite large. So that's actually quite important for things like getting the right distribution of fate H2 regions, because that's most of them.
Do you use that all information from the stellar particle distribution in the galaxy, or you forget about it completely?
We forget about it completely.
We could use it, but we didn't.
Okay, thanks.
Just to follow up on this, you said the Balmer dichromatic correction, for correcting for the H alpha emission doesn't work very well.
It doesn't. We do not say that it doesn't work at all, but at least now we can quantify where it works, under which conditions.
And it doesn't work sometimes because of geometric effects, or what's the main reason?
The APs are too high, right?
Excuse me?
The APs are too high, right?
I can't hear.
The ABs are too high?
Yeah, sure. And it also goes into some assumption that's about the distribution of dust, and also that H alpha and H beta react in the same way to each of the dusty regions along the line of sight. These are all assumptions that go into this kind of correction.
Why should they react differently? I mean, if you have H alpha and H beta going through the dust.
Yeah, but it's not exactly the same wavelength, right? I mean, it's close.
You have some extinction law, right? So something grain size distribution or something, and then you can change how it goes.
Yeah.
Do you want to mention?
Yeah. I mean, basically, the Bolmer correction works if your H alpha and H beta are coming from the same gas. And if your H2 region is too embedded, this is not the case. You're getting emission from different bits of gas because you're losing more of the H beta from the cluster than the H alpha. So for very embedded clusters,
Oops, sorry.
this fundamental assumption underlying the Balmer decrement correction just breaks down, and you get the wrong correction.
Mm-hmm.
So I mean, for clusters with AB and few, it works okay, but as you get more embedded, it just breaks down, which I think is not really used.
Do you want to say something about this?
Yeah, I had the exact same question as you.
Okay.
Because obviously we're looking at something. Because that's like, I mean, we know, I guess, but we try to forget that because this is like our optimal solution to this problem. So what, I guess the question is, up to what AB does this correction work? And then what, like, can we do better? Like, is Passion also going to be okay? Because we can get that with James Webb, or like, what like actually observable tracers can we use to get this right?
Yeah, that I cannot answer right now, but Eric Pellegrini, with this kind of data set, we are working on it to evaluating the limitation of this kind of correction and what other tracers might actually be better choices for tackling this kind of problem.
I just have a response to that, but then a different question, which is, isn't this about this not working in H2 regions, not in random places, right?
Yeah.
Right, okay. So it's not up to what AB, it's under what cluster conditions, I think, right? Okay. Okay, so now my actual question was, first of all, thank you. Like, when I was a PhD student working on stuff like this, I never thought the lasers was possible. So thank you. This is point one. But then the question is, one of the reasons I gave up working on polarization for the most part is because the grain alignment is so sensitive to the local conditions. And so you had a parameter in there for the efficiency of grain alignment, but I'm curious whether that depends on conditions, depends on grain size, depends on what?
On everything.
Yes, exactly.
I just avoided this topic completely, and this is just... these are here.
Right. But it's
which scales from 0 to 1, dependent on your thing. But so what we are doing is also a Monte Carlo run, as I've mentioned before, that we actually determine the direction and the magnitude of the radiation field, and from that we can calculate the spin-up efficiency for different grain sizes. And this allows us then to give some parameter which grain sizes can align with the magnetic field and which one remain randomized.
So for like really simple cases like the sub-millimeter polarization holes that were seen with the JCFT like 20 years ago, can you reproduce those?
Yeah, there's some publication from Blauer et al. 2016 that we did exactly that.
And it works.
In investigating the polarization holes and globules, for example.
So you showed these interesting results with the filament, but then you left me a little bit alone because, I mean, the structure of the filament is pretty regular in this simulation. The magnetic field is pretty regular, and then you said, well, it doesn't work. So if it doesn't work for this configuration, I mean, then if you go to even more complex configurations, it will also not work. So what's the reason that it doesn't work?
Yeah, the reason it doesn't work is the field strength, for example. I mean, here it's much lower than here, so you maybe don't have dust grains coupled on this side of the filament. and here you have. Then you have also all these kind of dense regions. So these grain alignment processes are also opposed by gas pinging onto the dust grains. So in a dense region you have also depolarization. And what happens is then, in order to trace the predicted or to match the predicted results, you actually need to have the polarization come from these regions. But what often happens is that here you have some depolarization where you have no aligned dust grains, and then the polarization comes from this side or the other, but not from the filament or the kink of the magnetic fields itself. And then you get a different kind of line profile, of polarization profile. So this is where we just find the right kind of profiles in these three distinct regions where all the parameters are in that way that the polarization comes actually from the filament itself and also from the region where the kink of the magnetic field occurs. But this also demonstrates that there's not one simple answer to the questions, that you really should do this kind of post-processing to get a feeling what's going on and make some reliable predictions there.
Yes?
Yeah, related to this. If you knew the strength, then it would be possible, right?
What strength?
The magnetic field strength. The principle, then you could kind of... Because you mentioned that you have different alignment mechanisms because of the different levels of magnetization. Yeah, that's not mechanisms, it's efficiencies. But, yeah, sure, yeah. But it also depends on the radiation field. So we assumed here some interstellar radiation field coming from the outside, but here we have also 3 star-forming regions, and they also contribute to the radiation field, and having the grain material, the size distribution, the field strength, and the radiation field in combination then gives you the answer. So it's not just a simple calculation dependent on the field strength.
Okay, I think time's up, so let's thank Stefan again. We need the microphone.
Yeah, thank you.
Thanks very much. You just put it on. Okay, so next we have Sarah Jefferson talking about giant molecular clouds under the influence of galactic dynamics.
Good morning, I'm Sarah Jefferson, a finishing PhD student at the University of Heidelberg. I'd firstly like to thank the conference organizers for the opportunity to speak here today. And I'd like to talk about the influence of galactic dynamics on molecular cloud evolution. So, of course, we're interested in molecular clouds because they're the sites where the vast majority of stars are formed. So their properties dictate the local conditions for star formation that, when averaged over the scales of entire galaxies gives us the global star-forming properties of those galaxies. So in order to understand how a galaxy converts its gas into stars, we need to understand the physics underpinning the cloud life cycle in those galaxies. So in recent years, high resolution sub-millimeter observations of the ISM have allowed observers to distinguish a strong relationship between cloud-scale observables and the large-scale galactic environment. So here, in a low-mass dwarf, a high-mass spiral, and our nearest major merger. And this behavior extends also to different areas of our own galaxy, where we see that clouds in the galactic center behave very differently to those in the outer galactic disk. So in order to incorporate this environmental dependence into a theory for molecular cloud evolution, a good place to begin is with galactic dynamics, as each large-scale galactic environment will host its own set of dynamics, which can be quantified by their individual timescales. So these are the timescale on which overdense regions of the ISM collapse under their own gravity, the timescale on which these regions are sheared apart by differential rotation, the timescale on which molecular clouds encounter spiral arms and galactic paths, the timescale on which molecular clouds encounter each other, and the time scale on which significant radial excursions are introduced to the orbits of molecular clouds by radial epicycles. So, considering the rates of cloud destruction associated with each of these timescales, we can calculate an average statistical timescale for cloud destruction or molecular cloud lifetime by linearly combining these rates. And the key result of this theory is that the influence of galactic dynamics on molecular clouds can be described by three properties of the large-scale environment. So the local degree of shear, the gravitational stability, and the angular velocity of the galaxy. So this allows me to examine how cloud properties vary in a dynamical parameter space spanned by these three axes, so here, here, and there. And we can actually divide the space according to which dynamical timescale is shortest. So which mechanism has the strongest influence on how molecular clouds evolve, whether that be shear, gravity, or epicycles here. So then the key trends to remember for the rest of the talk are that shear becomes more influential towards this top left-hand corner here, whereas gravity has a larger influence in this lower half of the space. So now I can compare this analytic theory to numerical simulations in the moving mesh code of PIPO. And the power of the analytic theory here is that it allows me to examine how the numerical cloud properties vary as a function of the dynamical environment. And because the analytic theory is so simple, including only galactic dynamics, I can use this as a framework to interpret the more complex physics in the numerical simulations. So in order to do this, I need to plot the numerical simulations in this space. And we find the dynamical environments at small galactocentric radii have on average a high degree of gravitational stability, and for a flat rotation curve as here, also a high degree of shearing. Whereas at larger radii, we find a much lower degree of stability, but for a flat rotation curve, still a high degree of shear. And we can draw a radial trajectory through the galaxy, which will fall along this line in the parameter space. So if I was interested in how clouds behave in these intermediate stability environments, then I would be averaging over the molecular clouds in this red annulus here. So these are the three isolated disk galaxies I've simulated, and I've ensured that they span as many dynamical environments as possible by manipulating their rotation curves and scale heights. And these are the numerical ingredients in the simulations, which I encourage you to ask about afterwards, as I don't have time to go into this now. So I can now connect the simulations to the observations by calculating the CO luminosity for every gas cell in the simulations, then projecting it along the line of sight and just applying a threshold to identify the clouds individually. And this gives me the cloud populations of each disk galaxy, which we find are overall remarkably similar. So here I'm just showing the cloud virial relations. However, in particular, the size and mass spectra of the clouds are almost indistinguishable for the 3 disk galaxies, and all adhere to the power law form given by the black line of observed clouds in the Milky Way. However, despite these similarities, I still see clear trends in cloud properties with dynamical environments. So, the cloud velocity dispersions appear to depend more heavily on the degree of galactic shearing, where for higher shear environments we see on average higher velocity dispersions, whereas the cloud surface densities appear to depend more heavily on the gravitational stability, where a higher degree of stability tends to correspond to lower cloud surface densities. So, for clouds in the Milky Way, for example, I would expect on average to see higher velocity dispersions and lower surface densities than those in M33, which falls more along this diagonal. So we can also look at the shapes of the clouds here, and we see a nice trend in the cloud ellipticity towards a higher influence of shear caused by the clouds being stretched out in the azimuthal direction by differential rotation. And we also see a similar trend in the Z component of the angular velocities of the clouds, where as the influence of shear increases, the clouds are more spun up against the direction of galactic rotation due to shear. And as we would expect for a trend caused by shear, the 2 other orthogonal components of angular momentum in the galactic mid-plane display no such dynamical correlation. So now we can actually look at the lifetimes of the clouds. And so if I track the clouds over time, I'm able to produce a merger history of the clouds over time. And I can isolate a disconnected component here, where you can see here, for example, a merging event and then a splitting event. And then we calculate the cloud lifetime by, at the moment, averaging over the lengths of all possible trajectories in the component. Yes, no. So here's how we're calculating the lifetime now, but this is an active area of investigation for me still. And so here are the cloud lifetimes I obtain, and we see they follow a similar trend to that given by the analytic theory in the background color here. However, universally, the analytic theory over predicts the absolute value of the cloud lifetime. And actually, this effect becomes more severe as the analytic prediction gets longer. So we interpret this as the influence of stellar feedback destroying the clouds on a shorter time scale than would be predicted by galactic dynamics alone. So in summary, the environment is important in how molecular clouds evolve. However, in all seriousness, we find that cloud properties and lifetimes follow clear dynamical trends. However, using galactic dynamics alone to predict the cloud lifetime will tend to overestimate it, as it does not include the influence of stellar feedback. So with that, thank you for your time.
Are there any questions for Sarah? Yes?
So it looks like the spiral arms are not a big part of the story.
Not yet.
Not yet. Do you expect that to also be the case if you include a strong bar?
A bar? You're asking if I expect spiral arms to form with a bar, or I expect
the bar to
to be...
the GC levels.
Yes. So within the analytic theory, we do have a term that accounts for the arms, and I would also use this same term to account for the galactic bar. So here we go. Okay. So yes, this term here is used to account for clouds interacting with spiral arms, and it could equally be used for a bar.
Yes?
So you mentioned that for the cloud identification, you have some CO cutoff.
Yes.
I was wondering if you could talk a little bit more about how you chose what cutoff to use.
Well, we just use a cutoff that corresponds to a molecular hydrogen column of 10 solar masses per parsec squared. If you use the CO2H2 conversion of Balato 13.
Okay, and last question, Sam.
Yeah, so have you explored how things change if you use a different algorithm to identify your clouds? Because, I mean, particularly for things forming along filaments, it's not immediately obvious how to break them up.
Yeah, I would be interested to examine how the properties, especially changes with environment, change as I lower and raise the threshold. Because I would expect, perhaps naively, for them to get stronger as I lower the threshold and weaker as I raise it. So that's something I would be really interested to do.
I think this is something maybe we should talk about back in Heidelberg, because I know Robin has played around with this a bit. There's some questions.
Okay, thanks, Sarah. Okay, next we have Vadim Semenov. He will talk about regulation of star formation from molecular clouds to galactic scales.
Hello, can you hear me? Yes. So yeah, thanks a lot. It's a great pleasure for me to be here, and I'd like to thank the organizers for giving me this opportunity to give a talk. So I'm Vadim. I just started my postdoc here at the CFA, and today I'll tell you about the work which I've mostly been doing during my PhD. So we have already seen a couple of nice pictures like this of sites where gas is actually converted to stars in the real galaxies, and I just wanted to show it again, just to remind us that how impressive and complex the structure of gas on the scales is. And so I myself work on galaxy simulations, and in galaxy simulations on the scales where stars form, we never see beautiful pictures like this. We usually see something like this. So none of this complex structure and dynamics of gas on scales where stars form can be resolved self-consistently, so modeling of star formation always require subgrid prescriptions in galaxy simulations. In other words, we need to tell our simulation what the star formation rate on the result scales is given the result properties of gas. And one common choice is to just parameterize the star formation rate in each resolution element with the efficiency per free-fall time, which and allows star formation on real gases to satisfy some criteria such as density or temperature thresholds or other thresholds. And then different simulations in different groups can make different assumptions about what these thresholds are and what the actual value of the efficiency is, but almost all this value is this efficiency is assumed to be constant in space and time. In contrast to this, theory tells us that star formation efficiency is not a fundamental constant of the universe. It actually strongly depends on properties of star forming regions, in particular on turbulence. For example, here, this plot shows the results of MHD simulations of cell-gravitating turbulence. And what these authors find is that star formation efficiency in turbulent gas decreases exponentially with this so-called viral parameter. So when support of turbulence increases compared to gravity, star formation efficiency becomes exponentially suppressed. And their similar prediction is coming from analytical models of star formation in turbulent gas. So we can use models like this as a subgrid prescription in galaxy scale simulations. And to do this, we need to know this velocity dispersion on the result scale. So we need a subgrid prescription for turbulence in simulations. Unfortunately, models like this exist. They are widely used in completely different contexts than aerospace engineering and simulations of terrestrial flows. So the idea there is that you can take hydrodynamical equations and filter them with some scale, and you'll get a new set of equations which describe the result flow and the evolution of turbulent energy on the result scales, and also terms coupling results on the result scales. And then you can solve this set of equations in the context of galaxy formation simulations, and you'll get something like this. So this is our simulation of a Milky Way-like galaxy, and this panel shows the predicted distribution of turbulent velocities in each cell using this subgrid model. So now we can use this field together with the gas density and temperature to predict viral parameter in each cell and use it to predict efficiency of star formation. And this is what happens. So this is the distribution of young stars. And we can see that they are forming along spiral arms. And then young stars explode as supernova, so they inject energy and momentum into the ISM. They destroy some of this dense gas and create this bubbles of diffuse and very hot and turbulent gas and create this overall dynamic evolution of the ISM on very short time scales. You can look at in more details on what predictions in terms of the star formation efficiencies is. So this is a map of the slope of star formation efficiency per free-fall time, and we can again see that star formation happens mostly along this dense and cold spiral arms, and this doesn't require any ad hoc thresholds, because automatically in diffuse gas is very well supported by thermal motion, so it has very high viral parameters, and according to this expression, it doesn't form stars at all. So next, the typical values in the dense and cold gas typical values of those dispersion are such that the average efficiency per freefall time is of order 1%, just like in observed actually star-forming regions. And again, this is the output of the model. And on top of this average value, the model also predicts wide variation of this efficiency even in dense and cold gas. So, for example, we can look at these two spiral arms. They have very similar density and they're both very cold. And so if we use just simple density threshold, we would assign the same star formation efficiency to both spiral arms. And you can see that in this model, one of the arms forms stars at very high efficiency, 10% per freefall time, while the other one doesn't form stars at all. And this is just because of the difference in turbulent velocities, which themselves reflect the differences in compression rates in these two spiral arms. Okay, if you look at more details, we can also see some other interesting features. So, for example, close to the center, in the center molecular zone, the efficiency per freefall time is also suppressed despite the high densities. And again, this is because of the high turbulent velocities driven by this strong shear. So overall, this shows that on locally on small scales, turbulence in star formation region plays a crucial role in setting this local efficiencies of star formation. And now we can ask different questions. So how it all propagates to larger scales, to how star formation in kiloparsec scale patches and on scales of tiny galaxies relates to what happens on scales of star forming regions and the process drive evolution on these scales, gas evolution on the scales. To do this, we can look at the evolution of gas in this plane of gas density and total velocity dispersion, which is both turbulent and thermal motion. So this shade gray contours show the distribution of gas in the galaxies, and this is very similar to what Sarah just showed in her talk, which would correspond to this dense part of this distribution. And this green shaded region shows the part of the phase space where the viral parameter is low enough so that gas can be star forming. And now in simulation we can just look at how gas evolves in this plane. So this how the trajectories of typical gas tracers look like in the ISM. So we can see that the gas rapidly evolves in this plane and it switches back and forth between star forming and non-star forming state in very short time scale. And this is because dynamical time scales are very short. And as soon as gas comes close to the star forming state, star feedback and other processes, dynamical processes that can destroy star forming regions, they do it very quickly and move gas back to a non-star forming state. And so as a result, it has to start cycle from the beginning. And this is why globally star formation is so inefficient, because in order to consume all the gas in star formation, each gas atom has to go through a large number of cycles through the star forming stages to be converted into stars. And in fact, we can use a picture like this to write down an analytical expression for depletion times, which is the ratio of gas mass and star formation rate, and we can express this time scale as a depletion time in star forming state only, divided by the mass fraction of gas in the state. So depletion time of star forming gas, it depends on properties of individual star forming regions, for example, on efficiencies per freefall time or the densities. And in simulation, it largely depends on our assumptions of the subgrid modeling of star formation. But the fraction of mass is shaped by the process that supply and destroy star forming regions. So it's a response to the galaxy to our assumptions. And we can express this ratio, this fraction as a ratio of typical time scales that gas spends in these two states. And then we can combine these two equations and get a simple expression for depletion times, which tells us that depletion time of gas is depletion time of star forming state, plus the total time that gas spends outside of star forming regions. And this time is very long because each cycle lasts for dynamical time scales as TNSF, and the number of cycles is very large. And it's large because of two reasons. So first of all, star formation and star forming state is very inefficient, so the depletion time of star forming gas is long. And at the same time, each individual duration of star forming stage is very short. So the ratio of these time scales give a very large number. So the situation here is very similar to soccer. So Harvard half of the audience already know about this, so for Heidelberg half. Soccer is also very inefficient, and players go back and forth very rapidly, so the dynamical time scales are very short. But at the same time, the average score at the end of the game is pretty low in high-profile competitions. So this means that the average time scale to score a goal is of order of is much longer than dynamical time scales. This means that soccer is very inefficient, and the origin of this inefficiency is very similar to inefficiency of star formation. So what happens is that when offense of one team goes to the other team, they face strong feedback from the defense. And as a result, the time scale that they spend close to the goals is very short. So they have low probability of scoring on each such approach, and they have to cycle through a large number of attempts before eventually they can accumulate enough probability and score. And exactly the same thing happens in the ISM. You can think about individual atoms as players going through star-forming regions and having low probability to become a star, to get into a star on each such cycle. And this equation just expresses the relation between all these different timescales in this continuous cycling. So we can use it, for example, to understand the dependence between global depletion times and local star formation in star-forming regions. So, for example, this shows the depletion time, global depletion time in simulations with different value of efficiency per free fall time assumed locally. So for this test, I just assume constant efficiency for some star formation thresholds. And you can see that there are these two different regimes. And this is because different terms of this equation depend differently on efficiency. So the depletion time of star-forming gas, by definition, scales inversely with efficiency. But at the same time, when stellar feedback is efficient in destroying star-forming regions, the lifetime of such regions also becomes inversely proportional to efficiency. So when efficiency is increasing, each star-forming region forms stars more rapidly. So stars inject proportionally more energy and momentum and destroy region proportionally sooner. So as a result, this dependence on efficiency cancels out in the second term, and only the first term depends on efficiency explicitly. So when efficiency is low, it dominates, and so depletion time, global depletion time also scales with efficiency. But when efficiency is high, the second term becomes dominant, and the global depletion time becomes independent of efficiency. And this is very interesting because it explains results of many galaxy simulations that show that when stellar feedback is efficient, global star formation rate becomes independent of the assumptions about local star formation efficiency. And this is, for example, shown here in this plot from fire simulation. So it's a simulation of the same galaxy with different efficiencies, and these lines show global star formation rate. And despite orders of magnitude variation of efficiency, the global star formation rate is the same. And this model explains the physics behind this self-regulation. And it's just the dominance of this non-star forming parts of the gas evolution in the ISM. Sometimes this self-regulation is interpreted as a global star formation efficiency doesn't matter because it doesn't have a global star formation rate. However, I think it's vice versa. It means that global star formation rate cannot constrain efficiency. So we need to find something else to understand which efficiency we need to use. And very strong constraints are coming from small-scale distribution and structure of the ISM. And one particular result I would like to highlight is this one. And this is because in about an hour we'll hear a lot more about observations like this. And we also heard some new exciting results in Stoke yesterday. And so what is shown here is the depletion time of gas in aperture centered on either gas peaks or H alpha peaks. So if we go as a function of the aperture size, so the averaging scale. So if we go to the large scales, we average over a large number of peaks, and we recover average galactic depletion time. If we go to smaller scales, gas and young stars become especially decorrelated, and the different branches in this so-called tuning fork, they start to separate. And the degree of the separation tells us about the degree of spatial decorrelation of gas and young stars on small scales. And in simulations we find that this value of local efficiency actually makes a strong difference in statistics like this. So this, and as I showed before, these three lines correspond to these 3 points which resulted in the same global depletion time. So on large scales they converge to the same global depletion time, but when we go to small scales, the structure of the SM becomes very different. How much time do you have? No? Zero? Okay. Just enough time to show one more slide. So another thing which constrains, which can be used to constrain star formation recipes is the so-called molecular Koenig-Schmidt relation, which is a linear relation, observed linear relation between star formation rate and molecular gas on kiloparsec larger scales. So it means that the molecular gas depletion time is constant, independent of molecular gas surface density. And in our simulations with the turbulent-based star formation, we can reproduce this constant depletion time of molecular gas. Or if we do the same simulation using threshold and density, which is usually used in galaxy simulations, we get much steeper relation. And the global star formation rate, again, is exactly the same, but in details it becomes very different. If you want to learn what's going on there, please ask me, and I'll stop here and just leave my summary.
Thank you very much. Are there any questions? Yes. Yeah.
So, can you comment on how you would think adding, I guess, a magnetic field to these galactic simulations, how that would affect the star formation efficiency and star formation rates?
In principle, they can affect all these time scales. So, for example, the effects of magnetic fields in star forming regions will may affect the local depletion times in star forming regions. However, the model which I used to connect the turbulent properties with the efficient per-field time, they were calibrated on MHD simulations of turbulence. So even though these simulations do not include magnetic fields, the star formation prescription implicitly accounts for magnetic fields.
What about? But that's just the local effect that doesn't do the.
Yeah. Okay. Yeah. So globally, it can also it can affect, for example, how if it provides like additional pressure. It can affect how quickly gas can go between star forming and non-star forming states, and then it will affect these two time scales.
If I may, can you paraphrase the effect of turbulence on the plot of the global depletion times and efficiencies? Like if you go back, back. Yeah, here. So
okay.
Here you were assuming a certain subgrid model for turbulence. So in practice, you are assuming certain scales for the injection of the turbulence and certain kind of amplitude.
Mm-hmm.
Can you describe what would change in this kind of relationship if you change aspects of the subgrid of the turbulence?
So here I used I did use subgrid turbulence to define star forming gas, but I used only a threshold in the variable parameter. So it was not continuously varied, but it was a threshold. But threshold nicely approximates this exponential dependence because variable parameter varies by orders of magnitude, and then they take exponent of this, it looks like a threshold. In principle, exactly the same relation we can get if we use density threshold or any other sort of threshold. The only thing which will change is the actual values of all these time scales, and so maybe like the value of which this situation happens, it will depend on the exact choice of these parameters. Not maybe, but it will. So I can show how.
Okay, so time is up. Thank you very much, Ben. And before the break, we
just have a couple of announcements. Let me. Thanks. Okay, so the first announcement is the schedule is different today than it was before, so look carefully at the piece of paper. And we're going to have a coffee break for 35 minutes or whenever I'm done talking. And then we're going to have the ITC colloquium will be in here, so there will be a lot of people. So if you want a seat, put your coat on a seat during the coffee break. So we'll hear from Diedrich at the colloquium. And then there's a lunch, which is just out in the world. So find a local friend to give you some ideas about where to go. And then don't go to Pforzheimer House after lunch. Come back here. And there's some more talks. And then we'll go to Pforzheimer House for 2 unconference sessions. And they say AM and PM, but that's wrong. It's like PM1 and PM2. Okay. So we'll sort out which ones go in what room later. But just write down your ideas during this coffee break. But more importantly, over here, I have some things. The first thing I have is a present for our Heidelberg friends to take back to Heidelberg. But first, we have to fill this lovely embossed Harvard leather pad with our names and our thoughts about the Harvard-Heidelberg meeting this year. And then Thomas and Henrik will take this to Heidelberg and be the keepers of this very important log of our fantastic activities. And I'm sure they will get it embossed with the Heidelberg logo as well. So thank you, Thomas, again, for starting these meetings. And then... Yeah, we'll put it out on the table, and there's a pen in there. And then for all of our organizing committee, we have these mysterious H mugs. H can stand for either Harvard or Heidelberg. So could everybody from the organizing committee come up here, please? Jody, you too. Thank you. Thank you. And then please take a mug and choose a color of pen. Here you go. Apparently there's a dispute over the purple pen. Okay. Somebody took blue. Catherine, here.
That's your favorite color.
I already did it. Okay, so on the bottom we're going to sign them all for everybody, so everybody can remember our fantastic work together, and everybody else can appreciate the work of this amazing committee. So take a bow, please. Thank you. And I think is that it for the logistics for what they need to know now? I mean, nobody's actually leaving the room.
Yeah. The only thing is the coffee will be picked up at 10:45, so start drinking now and make sure you get a refill before 10:45.
Yeah. Oh, Kara has a question. Yes. Yes. Oh, thank you, Kara.
Yes.
Thank you. That was the one thing, and Anna even suggested that a few minutes ago. So after the official ITC colloquium ends, before you go to lunch, the best place, unfortunately, for taking pictures is outdoors. So put your coat on and just assemble. There are some stairs literally right outside that door, and that is the best photo spot. And so we will take a picture there quickly, I promise. Okay? So we'll make an announcement. Just linger after the colloquium for a couple of minutes, and then we'll make an announcement when to go outside so you don't have to freeze. Thank you, Kara. Anything else? No, but thank you. This has just been so great, and so I look forward to the rest. Thank you very much. Bye.